All right, let me turn on the tape. So I've turned it on there. So we've officially begun. So of course, a week from today is our test. That will cover through, well, neither of these homeworks is on the test. It will cover through the last homework that was due last night, I guess, on composition and inverses. So everything from the last test up through that composition and inverses homework. And so that includes trigonometry, right? So right triangle trigonometry in particular is a big part of that. And then our review of important features of functions, but not so much, well, not anything about trigonometric graphs. These two homeworks, which is what we're started discussing last time. Transformations will be on there, but not transformations as applied to trigonometric functions. Remember, which gives us what are called sinusoidal functions. And these homeworks are all about graphing transformations of trigonometric functions. And but remember, most of the time on these homeworks, you're going to rely on either your calculator or your computer to make the graphs for you. Okay. Now, as far as Wednesday now, it's next Wednesday, I mean, for the test, it's the same format. So you can bring your survival card with you, right? So be sure you make out your survival card. And of course, you bring your calculator with you. And well, you probably need a calculator. So you want to be sure to bring some sort of calculator with you. And then we'll take the test in shifts like we did last time. So how did we do that last time? Was it A through M came first? Yeah. All right, so A through M will come first, and then we'll do the rest of the alphabet second, right? So A through M be here at 10, and then for the remainder of you, start at we'll start around 11:15. So be here by 11:15. So just like last time. And the sample test is posted as I mentioned last time. So there's an announcement there in WebAssign that says the sample test is posted. I do have the solutions ready, but I have not posted those yet. But I will sometime, probably this weekend. I'll post the solutions to the sample test. And so I'll send an email when those are posted to you. So be looking for those. Those will be in the Blackboard page, right, in the usual place, along with the sample test. And then now, on Monday, we will, in addition to regular lecture, we will go over some of the problems on the sample test. But the sample test is kind of lengthy, right? So we won't go through all of the sample tests on Monday. We'll just hit some highlights. And also, I will video also a discussion of some of the problems on the sample test. Because again, it's kind of a lengthy sample test. So some things we'll do in class on Monday, and some things I will just put on video. But I'm not going to even with the video, I'm not going to cover every problem on the sample test. But the solutions will be posted, right? So you will have the solutions to every problem, written solutions to every problem. So when I get that video ready, but it won't be till Sundays because I'm not going to have time to do it until Sunday. So sometime on Sunday, I'll tape that and then upload it to YouTube. And then again, I'll send an email when that's ready. So I'll remind you again in class on Monday that that video is available if you want to look at it. So that's kind of what's going to happen on the test. Are there any questions about that that you need to ask? A week from today. Yeah. Okay. So everything is the same as last time. So Amanda, you'll come at 10, right? Because yeah, on the Wednesday you'll come at 10. Yeah. What? No, Emil. I'm sorry. What was the question? Oh, so it's gonna next. What is due? The 6th. Yeah. So it's next week. Yeah. Right. A week from today. Right. Okay. So but Emil, not these homework. So it will cover the homeworks up through composition and inverses, but not these homeworks. Yeah. So it's, yeah, so what's on the sample test will be the material that's on the test. Yeah. So the sample test does not have any problems like the problems from these homeworks. Yeah. These are difficult to test on anyway, because as I mentioned, most times when we're graphing sinusoidal functions, transformations of trigonometric functions, graph them with a calculator or computer. We're not going to try to do that by hand, but so that's difficult to test on. Well, it'll be like analogous to the first sample test and the first test, right? Okay, so there's not going to be exact duplicates of problems, but there will be similar problems, right? Same type of problems. Yeah. So as always, the sample test is very effective way of preparing for the test. Okay. In addition to finishing your homework, but you've already finished your homework for all the homeworks that's on the test. If you finished the one on was due last night. Okay. So other questions in particular, quickly? Well, as they occur to you, you can always ask anytime during class. Let me see now. So I remember now what I forgot to cover last time. So that's why we ended up short so, in time last time. So I left off a piece of the notes here. So this is not really about trigonometric functions. This is about composition again of functions. And there are problems like this on the sample test, but there were not any problems like this in your homework, however. So the problems like this on the sample test, pay attention to those because you didn't get really practice with this on the homework, this particular part of composition, which is actually called decomposition, not composition. So I think so far in composition, we've been practicing with, you were given two functions and then you were asked to compose them, right? And then that would give you a third function. But often how we really work with composition, particularly in calculus, is kind of backwards. We are given a function and then we want to decompose it into two simpler functions. So we might be given a complicated function like x plus 3 to the 10th power. That's a difficult function to evaluate, and that's a difficult function to graph. But is everyone safe there? Sounded like there was someone was being mugged or something. Well, we're going to find out later what happened. Okay, so suppose you got this function x plus 3 to the 10th power, which is kind of, as I mentioned, kind of a complicated function to evaluate and to graph. But if we have to deal with a function like that in calculus, then it sometimes helps us to be able to break that function up, decompose that function into two simpler functions, so that when you compose the two simpler functions, you get the more complicated function. You see the idea? So I want to write down two simpler functions so that when I compose them, then I would get my more complex function. And then that allows you in calculus to sometimes to work with the more complicated function if you have it decomposed as two simpler functions. So what I want to do here is, so I'm going to lower the screen. So what I want to do here is write down the formula for two functions f and g. Hopefully they'll be simpler functions in some sense than this function h, so that when I compose f and g, I will get the function h. All right. Now, there's 4 examples in this problem, and there's A, B, C, and D, 4 parts. And I'm going to tell you ahead of time, the first 3 parts are really very similar. They're going to look different, but they're really very similar to each other. they're all decomposition problems. The fourth one is slightly different. All right, part D is slightly different. All right, so okay, so how can I discover what the formula for these functions f and g are? The way to do that, at least initially here, but once you've seen one example, then you'll get the hang of this pretty quickly. The way to think about this is there's really kind of two operations that are involved in this formula, right? One thing is you're adding 3 to x, you're adding 3 to your input. So you have that operation. And then the second operation is raising a base to the 10th power. So I'm going to break up this function h into those two separate operations. So I'm going to write down a function that just adds 3 to my input. So let's let f of x just be x plus 3, okay? And then I'm going to write down the formula for a function that takes a base and raises it to the 10th power. Well, that's easy. That would just be the function x to the 10th power, right? Where you just take your input quantity and raise it to the 10th power. So those are kind of my trial candidates for my my two simpler functions f and g. Now, what I want to happen, though, to check to see if these are correct is I want to compose these two functions, right? I want to compose these two functions and see if I come up with the function h. If I do, then I'm done, right? I will have accomplished what the instructions were here. All right. Well, let's just test this. So you do need to test this now. So let's see what happens. So if I take f compose g of x, remember that means f of g of x, right? That's what composition is. So make sure on your survival card that you have this written somewhere, right? So you won't forget. F compose g of x means f of g of x. Well, let's see. So let's work inside out here to simplify f of g of x, right? What's g of x? Well, that's x to the 10th power, right? So I can, instead of g of x, I can write x to the 10th power. And now what is f of x to the 10th power going to do? Well, you know, you calculate this, right? You evaluate this by plugging x to the 10th power in for x in the formula for f, correct? So what you get here is x to the 10th power. See, I substituted x to the 10th power for x here plus 3. Is that quite what I was looking for? Unfortunately not, okay? So I made a stab there, right? I gave it a try, and that didn't quite work. So let's just go back to the drawing board and let's try again. So this is sometimes kind of a trial and error process. Y'all see how I could fix this? I had kind of the right idea here, but how could I modify these candidates for f and g so that when I compose them, I will get the right result? Yeah, let's just try switching them, right? Okay. So you know, when you're trying to solve a problem by trial and error, right, and you you propose some solution, doesn't come out right. Sometimes just switching things around, correct, and trying again will give you the right answer. So that's what we're going to try here. So Emil suggests let's make f x to the 10th power, and let's make g of x x plus 3. Now remember, that could work because composition is not commutative, right? You compose functions in different order, you're going to get usually a different result. So let's see what happens now in this case. So this part is still the same. I still want to compose f and g, right? So f compose g of x still means f of g of x. But now here's where things are going to be different, because what's g of x now? Instead of x to the 10th power, yeah, that's going to be x plus 3, right? So inside these parentheses, right, I'm going to have x plus 3. So let me see if I can squeeze that in. And now what does the function f do? Well, it takes this input, right, and it raises it to the 10th power. So you're going to get x plus 3, right, substituted for x raised to the 10th power. And that checks, right? So that was the correct decomposition there. So we could let f of x be x to the 10th power and g of x be x plus 3. So it was the same idea that I started with, right? I had two key operations in this formula for h, adding 3 to the input and then raising a base to a power. And that's what became my decomposition. I just had to make sure that I labeled f correctly and I labeled g correctly. All right, now let's look at the next example. This one looks, so I want to decompose this function, square root of 2x minus 7. Not that complicated, right? But you know, a little bit complex in its formula. I want to decompose this also into the composition of two quote unquote simpler functions. How much simpler is a matter of debate, but somewhat simpler functions. All right, f and g, just like in this example. Now, initially, as I mentioned, these two examples look quite a bit different. Here you're taking this expression x plus 3 and raising it to the 10th power. And here you're taking a square root, which seems not the same, right? But really, this example and this example are very close to each other, because square root, you can remember, you can write square root as an exponent. Square root is what power? Half, right? So Amanda, see, we can rewrite the formula for h as 2x minus 7 to the 1/2 power. That's a really key observation. Always in calculus is to remember that square root means 1/2 power. So these two examples really are the same, you know, slightly different, but the format is the same, right? You have an expression raised to a power. Here we had an expression raised to a power. Same thing here, expression raised to a power. So I can use this as a guide here, or I can use A here as a guide to help me in B. So, well, what would it be there? So what should I let f of x be? Thinking of this as an example. Yeah, so x to the 1/2 power. Exactly. Just like here, it was x to the 10th power. Here I will use my exponent, right? To create this function. And then what about g of x? Yeah, that's going to be the expression that's raised to the power, right? Which is, in this case, 2x minus 7. And now let's just check that. So, so f compose g of x, that's, I want that to turn out to be h of x, right? So let's see if that works out. So we get f compose g of x, that's f of g of x, but g of x is 2x minus 7. And then what does f do with its input? It takes its entire input and raises it to what? The 1/2 power, right? So you have 2x minus 7 to the 1/2 power. But then you just have to remember, oh yeah, when I raise a quantity, when I raise a base to the 1/2 power, that's the same as taking the square root, right? So 2x minus 7 to the 1/2 power is really the same as square root of 2x minus 7. And that's it, right? That's what we wanted. That's the function h. So got it. Even C now, even part C is the same as part A and B, I claim. All right. Now that looks a lot different. There you have 1 over x squared plus 2x. But remember, when you take the reciprocal of a quantity, see here we're taking the reciprocal of x squared plus 2x, right? The reciprocal of x squared plus 2x is 1 over x squared plus 2x. So when you take the reciprocal of a quantity, you can also write that as a power. What power? Negative what? 1. Right, yeah. So we could write h of x here, this formula, as x squared plus 2x to the minus 1 power. We normally wouldn't write it like that, right? Okay. But in this case, it is helpful to think of it. So again, we're back to just like we had in B and C, right? You just have this quantity, this expression raised to a power, right? Okay. And so we know how to decompose functions like this now, right? Where the formula is just some expression raised to a power. It's easy to decompose, right? What would my f of x be in this case?
Inverse 1.
Right. So, but
Not
what? So what am I raising to the -1 power, Robbie? Yeah, x, right. Okay.
Dx.
Yeah, so you would just write x to the -1, and then the g of x obviously has got to be the rest of it, right? So that would be what?
The x squared plus 2x.
Yeah, x squared plus 2x. And now let's just check it. So is this really what we were hoping for? So f of x squared plus 2x, but the function f is just the reciprocal function. It just takes its input and raises it to the -1 power, right? So we get x squared plus 2x to the -1 power, which means we would normally write as 1 over x squared plus 2x, right? So see again, now the last example here of decomposition, this one is a little bit different. So this doesn't involve a power, okay? So here my function is h of x is sine of x squared plus 2x. So instead of 1 over x squared plus 2x, here we have sine of x squared plus 2x, okay? And so I want you to try to decompose this one, right? Okay, so how could you write, so I want you to just try this. So can you think of two simpler functions, hopefully, slightly simpler maybe, all right, f and g, so that when you compose them, you will get this original, more complicated function, right? So just experiment there on your paper, okay? Just write down a couple of choices there for f and g, and then just compose them, okay? Just compose them and see what you get. And if you get the original function, then that's it. You've done it, okay? So try this, or I'm gonna walk around and watch you there and see what you get there, okay? Sorry. Yeah. Yeah. Right there. Fine. Close it. See. That work? That work. Okay, now. Yeah, you can always check. The nice thing about these types of problems is finish that evaluation. The nice thing about these problems is what we're doing. Oh wow, that was so you got what's the other operation? Right. What's the other operation? Remember, sine is a function, so you have to have sine of something. So see, that seems very easy.
Yeah, sure, yeah.
Okay. All right, see, that also be very easy, but that simple decomposition with sign there, that throws students off a lot in calculus. Right, so I think everyone wrote it down nicely there. We can let f of x be sine of x, and then we can let g of x be x squared plus 2x, right? And then when we compose these two functions, we'll have f of g of x, but g of x is x squared plus 2x. And then when you apply f to a quantity, you just take its sign, right? So you would have sine of x squared plus 2x, and that's it, right? That's the original function h, okay? All right, so that topic is called, again, that's called decomposition, which is just kind of the opposite of composition, right? Trying to take a function and write it as the composition of two simpler functions. I don't have the, let me see though, in my, so here are the answers to the sample test, which I have not posted yet, but I will post at some point. And somewhere here in these, somewhere, let me see if I can find it, in these problems, there are going to be some examples of decomposition. So I just wanted to point those out to you as important problems for the, if I remember to put them in, yeah, here they are, 22 and 23. So those are important problems there for test, right? Because you may have composition problem on the test and didn't really have problems like that in them. Okay, so don't forget about those two problems when you're looking at the sample test. Even though it's long, make sure you look at those. Okay. Let me see if I can find. No, it's not this one. I'm looking for the right notes here that I did not think I didn't open. There we go. All right, let's look at a couple of applications of sinusoidal functions, because they do have lots of applications to them, and in different disciplines. And then we're going to look at quickly here. We'll look at graphs of the other trig functions, because we've been focusing on sine and cosine, but we do want to talk a little bit about the graphs of the other trig functions, so tangent and cotangent, and then secant and cosecant, right? But we're not going to graph those nearly as much as sine and cosine. All right, so let's look at these applications. These are pretty easy applications, but just to remind you that sinusoidal functions do have important applications. Here's one from sound. So this says a tuba player plays the note E and sustains the sound for some time. That's just to give us a little length of time here. That note is being played. It says for a pure E for this tuba, the variation in air pressure from normal air pressure is given by this formula. Okay, so you can see that's a sinusoidal function, right? Because it's a transformation of the sine function. So when you're hearing sound, right? What your ears are really detecting and then translating to electrical impulses, right, or nerve impulses that your brain can process for you. But what your ears are really detecting are variations in air pressure, okay, right? And then your eardrum, of course, senses those variations in the air pressure, then through a very complicated mechanism, right? Extremely complicated mechanism in your ear, all right? The oscillations in your eardrum, right, get translated into nerve signals, right? And then in ways that I'm sure are not well understood, right? Your brain can process those nerve signals, right? And your consciousness then hears sound, right? All right, but now what we do understand better though is when a particular sound is being played, right? What we can measure a little bit easier is the air pressure, all right, because we have devices to do that. And so if you measure the air pressure when this particular tuba is playing this note, right, and measure that over time, then you would get this function, okay, which is a sinusoidal function here. Notice that the air pressure there is measured in pounds per square inch, and the x here, the input, is elapsed time in seconds after the note begins played. Okay, so of course, again, that's a sinusoidal function, right? It's just a transformation of normal sine function. What is its amplitude? Right, yeah. So the amplitude there is really easy to discover, right? It's just 0.2. So when we try graphing this sinusoidal function, it's only going to go up to 0.2, right? Okay, and down to minus 0.2. And then what's the period here? So remember how we calculate the period. So how long does it take this curve to make one full cycle? Yeah, so what's the K value here? Yeah, we're going to calculate that in just a moment, Amanda. But this formula, remember, is 2 pi over K, where K is the coefficient of X, right? So what's the coefficient of the X here? Obviously, 80 pi, right? So we get 2 pi over 80 pi, and conveniently the pi's divide out, and we end up with 1 over 40, right? This is a second. So this curve is going to make one complete cycle in 1/40th of a second. All right. So this curve is going to be oscillating a lot, right? Well, you would expect that, right? When you're hearing a sound played, the air pressure is vibrating or oscillating frequently, right? Which is causing your eardrum to also vibrate quite rapidly as well. Okay. So you might expect the period there to be rather short. Let's make a graph of this and see what it looks like. So I've already built the graph, and the graph is kind of hard to make just because of the period is so short and the amplitude is short also. So when you're graphing this thing, you have to be careful about the portion of the X and the Y axis that you're going to graph. Let me see, I think it's this one, yeah. And so I've got this one graphed with a much different graphing window than would normally use. I've cut down on the y-axis considerably, okay, so that we can see the amplitude easier here, right? This curve goes down to minus 0.2 and up to 0.2, right? And then it doesn't look like it's oscillating when you see the graph, right? It doesn't look like it's oscillating that frequently, but notice the intervals on the x-axis are very small, right? This is 0.01, this is 0.02, this is just 0.0c. So this thing is really oscillating very rapidly, okay, along the x-axis. So if you were to graph the x-axis from 0 to 1, okay, this thing would oscillate very rapidly, okay. It would be actually even hard to look at the graph very easily, okay, because it would be going up and down so quick. By the way, that number of oscillations that the curve makes in 1 second, that's called the frequency of the sound. All right, and so let's calculate that. That's easy to calculate if I can find the right screen here. All right, so the frequency of V is the number of cycles completed in 1 second. Okay, so you see it completes a one full cycle in 1/40th of a second, in 1/40th of a second, because that was the period, right? So how many complete cycles does it make in 1 full second? How would you do that? Any ideas here? So it makes 1 full cycle in 1/40th of a second. So how many full cycles is it going to make in an entire second? What? 40, right? Okay, sure, right? Okay, it makes 1 cycle in 1/40th of a second. So that means in 1 full second, it's going to make 40 complete cycles, right? The way you compute that is just take 1 over the period. That's the frequency. So you might want to remember that for your physics class. Okay, 1 divided by the period is the frequency. And so in this case, we have 1 over 1 divided by 40, which indeed gives us 40. So the frequency of this particular sound is 40. If you want to make the, so we've seen the graph, right? So we relied on the computer to make this graph for us. You can just use your intuition to answer this question. If the tuba player increases the loudness of the note, what in that equation is going to change? So what would you change about that sound to make it louder? You don't want to change the note though, okay? So what would you change in this formula to get a louder sound? Same sound, so your brain will detect it as being the same note, but it's going to sound louder to your brain. Yeah, Amanda. The amplitude, that's it, right? It's just exactly sure. Right. So if you increase the amplitude, you're going to increase the loudness of it, right? But if you don't change the period or the frequency, you're not going to increase the sound itself, the note, right? The amplitude change the loudness. Here's another place where we have a quantity that's oscillating. So it's increasing and decreasing, again, quite rapidly. And so that's useful. That's useful to our brains, right? So that we can hear things. So that's a lucky break for us, right? And here's another case where a quantity oscillating is quite useful to us, all right? So if you have a normal household circuit, right, that's going to be a 110 volt circuit, and that works with what's called alternating current, right? Not always that way, by the way, but that's how the circuits work now, right? What's called alternating current. And so what that means is that current on that circuit is going to the voltage on that circuit is going to oscillate. It's going to increase and decrease. And that oscillation is what allows electrical devices to work. Okay, so to make use of the electricity and work. So here is the equation for the voltage on a 110 volt household circuit, right? And E is the voltage there, measured in volts, and X there is again elapsed time seconds, right? So here we have again a transformation of, in this case, the cosine curve, right? But this still counts as a sinusoidal function, right? So let's see what's happening to that voltage on your alternating current circuit, right? Like you plug all your devices into. So let's see, what is the amplitude there? Very easy to see. What? 155, right? Okay. So what that means is approximately the maximum voltage on that circuit is going to be what? 155, right? And the minimum is going to be negative 155, right? Okay. Notice that the voltage is fluctuates between positive and negative. Okay, that's why it's called alternating current. All right, and so you can't have you can measure voltage as negative. And let's see, what about the period then? Of course, so that should be easy to calculate too. That's going to be just what? So 2 pi over Hannah, what? 125. That's what you did. And so that just becomes, yeah, 1 over 60, right? So the frequency here is what? 60, right? Okay. So you may be wondering why is this called a 110 volt circuit? Because the amplitude is 155. It goes up to 155 and goes down to minus 155. So why do we call it a 110 volt circuit? Why isn't it called a 155 volt circuit, right? Okay. Let's look at the graph and I can give you kind of the explanation for that. So you know already what the graph is going to look like, right? It's going to just be this oscillating cosine curve. So there's the graph of it, all right? And so again, it goes up to as high as 155. Notice since this is cosine, it begins at 0 at its maximum, right? 155, then it dips to minus 155, and then and so on and so forth, right? Okay, and it takes it what, 1/60th of a second, right, to make one full cycle. So apparently from here to here is 1/60th. I don't know what 1/60th is in decibels. Must be 0.01667, right? Okay, and then and ultimately make 60 of those complete cycles, right, in 1 second. If you take the absolute value of the voltage, see, sometimes the voltage here is positive and sometimes the voltage is negative. If you take the absolute value of the voltage, you'll only get positive values, right? Because absolute value only comes out positive. So what would happen is if you graph the absolute value, these negative parts of the curve, they would shift up. They would become positive. So you would have peaks here again instead of valleys. And then if you look at the average then voltage on the circuit, the average voltage on the circuit, in that case, it turns out to be 110. So that 110 is an average of the voltage that's on the circuit. If you think of the negative voltages as also being positive, all right? If you think of the negative voltages as being negative, took the average, you'll end up with an average of 0, right? Because this curve is half the time it's above 0 and half the time it's below 0, right? So the average would be 0. But if you think of the negative voltages also as being positive, you get an average of 1 approximately. So that's where the 110 comes from. The signature sheet, yes, okay. there was a big debate. This isn't a very nice movie, but I forgot the name of the movie. It's a movie about this. There was a debate between Thomas Edison, and Tesla, who the car company is named after, right? About whether to use alternating current or it actually wasn't Tesla, it was Westinghouse, but Westinghouse got his ideas from Tesla. About whether to use direct current, whether that was the more feasible way of powering devices, or using alternating current. And Edison was a opponent of direct current, but see, Edison lost. Okay, so, and Westinghouse won that battle, and that's how the company Westinghouse began, right? And he made a fortune that way. All right. Now, I do want to look at we do need to look at some of the graphs of the other curves. And if I can find my correct notes. So, so let's talk about those other functions a little bit, and then we'll look at their some of their graphs. So let's start with tangent, because that's the one that's going to be the after sine and cosine. That's the one that you would see most frequently. And I just want to remind you that tangent, remember, you can also define that as sine divided by cosine. So always keep that in mind. Tangent you can compute as sine of x divided by cosine of x. And when you think of tangent in this way, that gives you a little bit a better understanding of what the graph of the tangent is going to look like, okay? Because the domain of the tangent function is not going to be all real numbers. The domain is not going to be all real numbers. For sine and cosine, domain is all real numbers, but not for tangent. So tangent has some missing values in its domain. And the values that are going to be missing from the domain is where the cosine is 0, remember, because you cannot divide by 0. So, so whenever cosine is 0, those numbers we have to exclude from the domain of the tangent, because we would end up dividing by 0. So we just have to remind ourselves, where is the cosine equal 0? So do we recall where cosine is 0? Where's the first place cosine is 0? Say that again, what? No, not at pi. First place. Cosine. Cosine of 0, where does cosine begin? At 0, cosine is what? 1. And then remember, it drops, and eventually it hits 0. So where's the first place it hits 0? What angle do cosine? Pi over 2, right? Yeah. So pi over 2 is the first place where cosine is 0. And then every pi units after that, cosine is also 0. Okay. So if you take pi over 2 and add or subtract any multiple of pi, so if you go any multiple of pi to the left or any multiple of pi to the right, you also get cosine of 0. So those numbers cannot be in the domain of the tangent function, because to be dividing by 0, right? So the domain of the tangent function is all real numbers, except you have to throw out pi over 2 and then pi over 2 plus any multiple of pi. So 3 pi over 2, 5 pi over 2, 7 pi over 2, or minus pi over 2, minus 3 pi over 2, minus 5 pi over 2. Those numbers are not in the domain of the tangent. So when you graph the tangent, you don't get a nice, pretty curve, okay? You get a bunch of branches like this, okay? So you get a curve that has lots of branches in it. Looks like this. So it's not an easy, curve to graph by hand at all, right? And notice that again, the curve does not cross over pi over 2 or 3 pi over 2 or 5 pi over 2. It doesn't cross over any place on the x-axis where the cosine is 0, because you cannot divide by 0. So you have breaks in the curve at all of these locations: pi over 2, 3 pi over 2, 5 pi over 2. Any place where cosine is 0, you're going to get a break in the graph of the tangent. Otherwise, you just get these increasing branches. Okay, the curve is increasing from left to right. You get these increasing branches. It does cross the x-axis several places. Okay, so notice each one of these branches, in fact, is going to cross the x-axis. So you get lots of x-intercepts. The x-intercepts are going to occur where the sine is 0, right? Okay, because again, tangent is sine divided by cosine. So this fraction will be 0 where sine is 0. Where is sine 0? Well, where's the first place sine is 0? Sine 0, right? Okay, and then it's 0 every pi units after that. So sine is 0 at 0, it's 0 at pi, it's 0 at 2 pi, and so on and so forth. So the tangent function is going to have a bunch of x-intercepts, the same place where the sine function does, in fact, at 0, pi, 2 pi, 3 pi, and then at minus pi, minus 2 pi, and so forth. So just get a curve that looks like this. Cotangent, of course, as you can expect, going to be very similar, right? Remember, cotangent is cosine divided by sine, not sine divided by cosine. So cotangent is kind of opposite of tangent. So you just flip the x-intercepts for the cotangent. They're going to be where cosine is 0. Well, we just discussed that. Cosine is 0 at pi over 2, and then plus any multiple of pi. And where is the cotangent going to have an x-intercept? Where is it going to cross the x-axis? It's going to cross the x-axis. I mean, sorry, that's where it's going to have an x-intercept. What numbers are not going to be in the domain of the cotangent function? Any place where the sine is 0. So where's the sine 0? It's always 0 at multiples of pi. Let's take a look at the graph. It's going to look very similar to the tangent. Looks like this. Except notice it's decreasing instead of increasing. So again, where do you have these breaks? You have these breaks in the graph wherever the sine is 0, wherever sine is 0. Where is sine 0? At 0, pi, 2 pi, minus 2 pi. So the cotangent curve doesn't cross over those places on the x-axis. And where do you have x-intercepts? Wherever the cosine is 0. So that would be pi over 2, pi over 2, pi over 2, minus pi over 2, minus 3 pi over 2, etc. Notice cotangent is decreasing. So instead of increasing left to right. Tangent's increasing from left to right, but cotangent is decreasing. Wow, what about secant? My goodness, what could secant? Graph secant, what could that possibly look like? Remember, secant is the reciprocal of the cosine, right? Secant is the reciprocal of the cosine. So that gives you an idea of what numbers are not going to be in the domain. In secant, you cannot have any number in the domain where cosine is what? 0. Whereas cosine 0, we just discussed that. At pi over 2, and then pi over 2 plus any multiple of pi. So 3 pi over 2, 5 pi over 2, minus pi over 2, minus 3 pi over 2, etc. Those numbers not in the domain of the secant function. Fortunately for the secant function, you don't get any x-intercepts. So the secant function never crosses the x-axis. Why is that the case? Because to have an x-intercept, that means this formula would have to be equal to 0. But to make a fraction equal 0, what has to be the case in the fraction? What has to be 0? No, the denominator is where it won't exist. But to make it 0, what has to be 0 in the fraction? Fernando, so you almost had it right. No, the top has to be 0. Yeah, for a fraction to be 0, the top has to be 0. But 1 is never equal to 0. It's just not, it's 1. So you don't have any x-intercepts. So secant, when you graph it, never crosses the x-axis. All right, so it does give you a nice graph, though. Looks like this. All right. It just has a bunch of U's in it. These look like parabola shapes, but these aren't really parabolas. They're not quite the same shape as a parabola, but they have that U shape. All right. So notice you just get these alternating branches, right, which are shaped like U's. And again, what's missing from the domain? So why does the curve not cross over any of these lines? Because this is where the cosine is what? You cannot cross over where the cosine is 0, right? Cannot have cosine be 0, because then you would be dividing by 0 in its formula. So where's the cosine? 0, pi over 2, 3 pi over 2, minus pi over 2, etc. Wow, this is kind of interesting. Notice that for the secant, not only does the curve never cross the x-axis, it never even gets close to the x-axis, right? What's the smallest positive number that the secant becomes? 1, right? Yeah. And then the largest negative number it becomes is -1. So it never even gets close to the x-axis, much less crossing. Cosecant is going to look very similar, right? But remember, cosecant is 1 over sine of x. So what's going to be missing from the domain of the cosecant? You cannot have what? Sine of x. You don't want what? You don't want to be dividing by 0. So anywhere sine is 0, that's not going to be in the domain of the cosecant function. Where is sine 0? What's the first place? 0. Yeah, sine of 0 is 0. And then pi, 2 pi, 3 pi, any multiple of pi. In the negative direction as well. Minus pi, minus 2 pi. So when you make a graph of cosecant, you get a curve that looks like the secant graph. You've got these alternating U's, okay? But the graph never crosses over where x is equal to pi. See? Graph has a break at minus pi, 0 pi, 2 pi, 3 pi, and so forth. No x-intercepts, never touches the x-axis. In fact, it never gets below 1 or above -1. So no x-intercepts there. Well, we can apply transformations to tangent and cotangent and secant and cosecant. The only ones we're going to think about here, though, are stretches, horizontal and vertical stretches. So we're not going to look at shifts for tangent, cotangent, secant, and cosecant. Oh, there's one thing I forgot to mention. These curves also are all periodic. They repeat, right? Okay, they all repeat. And so see the tangent, right, is just this same branch repeating. So what's the period of the tangent function? How often does it repeat? Every, how many units there? See, this would be, this branch is 1 cycle, although it's really not oscillating because it's always increasing, right? But this counts as 1 cycle of the tangent function. So how long is that cycle? Stretches from what? Minus pi over 2 to pi over 2. That's a length of what? That length. From minus pi over 2 to pi over 2. That's pi, right? So I didn't write it down here, but I should have. The period for, oh, I did. Okay. The period for the tangent function is pi, not 2 pi, but pi. Okay. The tangent function repeats every pi units, and so does the cotangent function. It repeats every pi units as well. For the secant and the cosecant, though, their period again is 2 pi. All right. So they have the same period as the sine and cosine, right? So for the secant, it repeats every 2 pi units. A cycle for the secant would be 1 up u and 1 down u. That's one up u and 1 down u is one full cycle that occurs over 2 pi units on the x-axis. And for a cosecant, the same. The period is also 2 pi. So if you make horizontal and vertical stretches, you might be affecting the period, and you can calculate the period though the same way that we did for sinusoidal functions. For tangent and cotangent, right? If you multiply the x by a constant, you're going to affect the period. What's the new period going to be? Just take the old period, which is pi, and divide it by k. So don't take 2 pi divided by k, because for tangent and cotangent, period is pi. For secant and cosecant, if you make a horizontal stretch, you just take the old period, which is 2 pi, and divide it by k. Of course, what's this coefficient a going to do in all of these examples? If you multiply outside here by a constant, what does that do? What kind of transformation is that? Yeah, that's a vertical stretch, right? Okay, but tangent and cotangent and cosecant and secant, they don't have anything called amplitude. All right, so you do stretch the graph, but we don't try to compute amplitude for these curves. All right, so you know, you can make a vertical stretch to these curves, but it doesn't have a special name. Let's see if we can think about what these are going to look like, but we're not going to try to graph these by hand because that would really be tedious. All right, so what's happening with these functions? So this is kind of like the graph of tangent, right? But what's different here? Well, the main thing that's changed here is the period, right? So what's the new period here going to be? Pi, right? Not 2 pi, because the period for the tangent is pi. So you take pi over, divided by this value k, you get 2, pi over 2, all right? So so you get a branch here of the tangent curve every pi over 2 units when we graph this, instead of every pi units when you graph the normal tangent. You are going to have a vertical stretch, all right? You are going to have a vertical stretch. So you're going to be stretching this graph by a factor of 3. That's very hard to kind of recognize in the graph, though, but it is stretched by a factor of 3. Let's take a look at that. Let's take a look at what that thing looks like. So I think I've got this one somewhere here. It's not that one. Let me turn the right one on. There it is. Okay. So you just get all these branches, right? That is tangent, right? Because remember, tangent has these increasing branches, right? And remember, they're increasing. For tangent, the branches are increasing. And we get a lot of branches here because we changed the period, correct? Okay. The normal period was pi, and we changed the period to pi over 2. So that means we doubled the number of branches. This graph. Let's try this second one. So what's happening here? There's cotangent. So when you graph this, you get a bunch of branches just like this. All right. But what's different about this one than the normal cosine, normal cotangent curve? What now? It's inverted, right? Okay, so we've rotated it. So what effect is that going to have, Fernando? The original cotangent, remember, it's opposite of tangent. So instead of the branches going up on the original cotangent, the branches are coming down from left to right. So when we rotate it, they are going to be going up. Okay, so the branches will be increasing just like with tangent. And what's the period here? Well, the normal period is pi, and but we're changing that by dividing it also by pi. So we get what? 1. So we get one branch, one of these branches every 1 unit on the x-axis. Let's see if that's correct. I'm dubious about that. Let's see if that's what that really comes out looking like. So let's try this one out. We can't put all these on together because this looks like spaghetti when you do that. But okay, there it is. So see you get a lot of branches there, right? Because we really shortened the period quite a bit. And the branches are increasing from left to right. Normally they would be going down from left to right, but they're going to be increasing from left to right because of the rotation here. Let's see, does this have a branch every 1 unit? Let's start at 0. So 0 there, and we go over to 1. Yeah, I think that is 1 branch is there, right? And then from 1 to 2, you get another branch, and then from 2 to 3, you get the 3rd branch, and so on and so forth. Yeah. Okay. So we get 1 branch there every 1 unit, every 1 unit x-axis. Nice. You remember what cosecant looks like? So that was a bunch of what? U's, right? Okay, alternating. All right. So you have a u pointing up and then u pointing down. What have we changed here? Yeah, what's the period? It's normally 2 pi, but in this one we've changed it by dividing by what? 2. So it's just pi, right? Okay. So we'll get 1 full cycle every pi units along the x-axis instead of every 2 pi. So that means that pi units along the x-axis, you'll get 1 upward u and 1 downward u complete. Okay. And we also have here a vertical stretch. Hard to describe though what that's going to do, but we do have a vertical stretch there. Okay. So somehow the curve is being stretched vertically. Let's see. We guessed that right. Looks nice there, right? So we have lots of those U branches, correct? Okay. In fact, twice the number because we reduced the period from 2 pi to pi. So let's see if we can figure out how. There's 1 U branch, right? And then here's the second one. So where does this end? This should be, what should that be on the x-axis? About what? About 3, which is pi, correct, right? Because we're supposed to get 1 full cycle every pi units on the x-axis. Oh, I can't point at that. So does that look like that's a little bit more than 3? I think so, right? There's 3. So yeah, so it looks like we've gotten both branches there in a little bit more than 3 units, which is pi. 1 upward u and 1 downward. What about for secant of 2 pi? No vertical stretch, that's a relief. But we have changed the period again, right? What's the new period here? What, Amanda? 1, right, yeah, okay. So when you graph this, again, this is secant, so you get the alternating u's, right? So that means you're going to have 1 upward u, 1 downward u in 1 unit on the x-axis. Let's see if that happens, because the period is 1. Wow, this is hard to look at. So let's look at these two. This, it looks like these branches should have started at, wow, I can't tell. Where is that? Maybe we should start at 0. Let's start at 0. So if you start at 0, you get what? First, this half of the u, right? And then you get the, so you get the right half of the u, and then you get the u pointing down, and then you get the left half of the u up to here, Where does that end? Oh yeah, right at 1. Yeah, so 1 period indeed is 1. So I think on this homework, which is more trigonometric graphs, this is not a very long homework. Let's look at it. And I think you're just asked to do some graphing here. And so you really want to make use of, right, of either your graphing calculator or Desmos to help you make the graph. Remember, you can get to Desmos by opening the description, and there's the link to graphic tool. So if you make those graphs, you can pick out, I think, which should be the correct one. Okay. All right, let's we're through talking about graphs of trigonometric functions, but we're not through talking about trigonometric functions because we have not talked about inverses of trigonometric functions, and there's a good reason for that. And we'll discuss that in just a second here. How do we get what are inverses of trigonometric functions look like? All right, so let's take a break here. We'll come back at maybe about 11:20, and we're going to start talking about inverses of trig functions. Let me pause the recording. We're going to end the week here on a high note because this, did everyone get to sign the, got to sign it? Cross that man. All right, we're going to end the week here on a high note. You guys at home, listen also closely because we're going to talk about a really key topic here. And this is inverses of trig functions. Now, this is going to be a little bit sloppy for the reason I'm getting ready to say, and that is the 6 trig functions as we know them do not have inverses. Okay, all right. So none of the trig functions naturally are going to have inverses. They're not one-to-one functions. That's very easy to see that they don't have inverses because they're periodic. So that prevents them from having really inverses the way we described inverses when we were discussing inverses a couple of weeks ago. For instance, the sine curve, right? Okay, here's a graph of the sine curve. It's periodic, so that means that it repeats its output values every 2 pi units. So if you're, anywhere on the x-axis, right, at any point on the x-axis, if you just add 2 pi to x, right, and compute sine of x and then x plus 2 pi, you'll get the same y value, right? You'll get the same output value. So that means on this curve, right, you have lots of points that have the same y coordinate, lots, right? Infinitely many, in fact. So so the sine curve itself, just the way it was defined, will not have an inverse. It's not a one-to-one function. But that's really an inconvenient fact, okay? Because inverses are going to be really useful to us and important to us. So we would like the sine curve to have an inverse, all right? So so what we have to do here is get a little bit clever so that we can make sure that the sine function does have an inverse. All right, so here's what we do, okay? Since the original sine function doesn't have an inverse, what we're going to do is create a new function called the restricted sine function. Restricted sine function that's almost as useful as the sine function, but does have an inverse. So we're going to monkey around with the sine function, in other words, right? So that it will have an inverse. And the way we monkey around with it is we're going to create a new function by restricting the domain. Now, the domain of the original sine function is all real numbers, right? Okay. And so, but our our new restricted sine function, its domain is only going to be from minus pi over 2 to pi over 2. Okay, so we're going to create this brand new function called the restricted sine function. Now, it used to be in books that the restricted sine function was given a different name. Okay, all right, so that you could distinguish it from the original sine function. But that practice is kind of stopped. All right, and so so you have to kind of get accustomed to just knowing from context if you're working with the original sine function or with the restricted sine function. All right, their only difference is their outputs are the same. All right, calculate outputs the same way. The only difference is the domain of the restricted sine function is, instead of all real numbers, it's only minus pi over 2 to pi over 2. So there's not, in a sense, not a huge difference between the restricted sine function and the sine function. Okay, but the effect of that difference is the restricted sine function will have an inverse. It does have an inverse. All right, let me show you why that's the case. All right, so you know, when you graph the original sine function, right, its domain is all real numbers, right? So it extends, that curve extends, you know, that oscillating curve, it extends infinitely to the right and infinitely to the left. But with the restricted sine function, it only goes from minus pi, its domain is only from minus pi over 2 to pi over 2. So when you graph it, you get the graph of the sine curve, except it's just cut off, right, from minus pi over 2 to pi over 2. And for that little domain, from minus pi over 2 to pi over 2, the restricted sine function does have an inverse. It is 1-to-1, because notice it's always increasing. This part of the sine curve is always increasing. So you don't have any repeated y values. So this curve will have an inverse. Now, what's the inverse? What's the inverse going to look like? Well, we can kind of imagine it, right? So remember the blue curve here, that's the original sine function, except we've restricted it. So we've cut its domain down to just minus pi over 2 to pi over 2. And I put in here the 45-degree line. And then let's think about rotating the blue curve around the 45-degree line. And when you do that, you get this black curve that looks kind of like this. So here's the graph of the inverse of the restricted sine function. So the restricted sine function does have an inverse, right? And it looks something like this. The graph is not what's really all that important to us. We're really not going to be using the graph of the inverse, all right? But there's what it looks like. So it's got, you know, a nice curve, right? But nothing special. All right, now, let me remind you, for the restricted sine function, which again, we don't give it a separate name, so it looks like the sine function, right? Remember, its domain is what? Only what? Minus pi over 2 to pi over 2. Okay, not all real numbers, just minus pi over 2 to pi over 2. What's its range? Well, it still goes on the y-axis from -1 to +1, just like the original sine function does. So it has the same y values as the original sine function. Now, what about for the inverse function? All right, so here's our name for the inverse of the restricted sine function. You can call it sine -1 using that -1 notation. All right, but this function actually has been in use long before modern function notation was created. So this the inverse of the sine function has a special name. Also, it's called the arc sine function. These two names mean the same thing. Okay, this is the old-fashioned name for the inverse of the sine function, and then sine -1 is kind of the modern notation for inverse of the sine function. You decide which one you like best. Okay. I'll tell you what's going to happen though. Over time, you'll start using this more frequently. All right, it's more convenient to say arc sine. But remember, that just means inverse of the sine function, but it's not inverse of the original sine function, right? It's inverse of what? The restricted sine function. And that's really important. Okay, I know that sounds like that's kind of, kind of just a little catch there, but it's actually an important distinction. All right. And here's why this distinction is really important. What is, all right, so there's the restricted sine function, there's its domain and range, there's the graph at least of the arc sine function, right? Or the sine inverse function, right? What is the domain and range going to be for the inverse function? Remember, when you create an inverse, what do? What are you flipping? You're flipping the x and y's. So that means that the domain and range are going to get flipped here for the inverse. So the domain for the inverse function is going to be the same as the range for the original function. So that's numbers between -1 and 1. And the range for the inverse function is going to be the domain for the original function. So that's numbers between -π/2 and π/2. So this is the range for the inverse, and this is the domain for the inverse. All right, I really have to stress the importance. You have to remember when you're working with the inverse sine function, it's very important to remember its range. I know that seems like just kind of a technicality here, right? But it turns out to be crucial to use the inverse sine function properly. Remember its range. Range are only numbers between -π/2 and π/2. So when you're using the inverse sine function, you can put in what size number? What number can you put in to the function? Anything between -1 and 1. Okay, that's the domain of the inverse sine function. What do you get out as an output? Something between what? -π/2 and π/2 only. Okay. Remember, the inverse is opposite of the original. So the inverse, you put a number in, you get an angle out, right? For the sine function, you put an angle in, you get a number out, right? For the inverse, it's opposite. You put a number in, you get an angle out. All right. So here's kind of what I just said in a mathematical statement. So if you write y equals arc sine of x or y equals sine inverse of x, these two mean the same thing. That's true if and only if the sine of y is x. See, remember, how do inverses work? You flip x and y. So if sine of y is equal to x, that means arc sine of x is equal to y. Or sine inverse of x is equal to y. And for the arc sine, you can only use inputs between -1 and 1, and you get angles as outputs between -π/2 and π/2. Let's actually see if I can find one here before we talk about the other trig functions. Let's scroll down and see if we have an example. There's one. So let's just try this one first to kind of solidify your or help your understanding of the arc sine function or the sine inverse function. So remember, the way the sine inverse function works is you put in a number, right? And you get out a, what sort of creature? Angle, right? Because in the sine function, it's opposite. You put in an angle, you get out a number. Now, what kind of number can you put in? It has to be a number between -1 and 1. Well, 1/2 is certainly between -1 and 1, so we're okay. Now, how do we figure this out? How do we figure out what is sine inverse of 1/2? Because we don't have a formula for sine inverse, right? So how do we evaluate this? Well, here's the way. Look, if sine inverse of 1/2 is equal to some number y, that means that's only true if sine of y is equal to 1/2. See? If you put a number into the inverse function, get a result back, that means that sine of that result has to be whatever number you put into the inverse function. So if arc sine of 1/2 is y, that means sine of y is equal to 1/2. Now, how does that help you? Well, you're pretty good with the sine function, so I bet you can figure out, I bet you can figure this out. What angle has sine 1/2? Just think about it for a moment. What angle has sine 1/2? Now just remember that from your memory. Well, let's see. Is it 0? Sine of 0, is that 1/2? No, what sine of 0? No, sine of 0. Where does 0 start at? Sine of 0 is 0. Yeah. And then let's go to the next special angle, which is pi over 6, 30 degrees. What sine of pi over 6? No, that's sine of pi over 4. So pi over 6, 30 degrees. What now? 1/2. It's 1/2. That's right. Remember, okay, so I keep, I remind you again, how can you compute sine of special angles? Sine of 0 is 0. That's square root of 0 over 2. Sine of 30 degrees is square root of 1 over 2. What's square root of 1? 1, right. So that's 1/2, right? What about 45 degrees? That's square root of 2 over 2. What about 60 degrees? Keep going up, right? So square root of what's next? What? 3 over 2. And then 90 degrees is square root of 4 over 2, but square root of 4 over is 2. So you have 2 over 2, which is 1. Right? Remember that. You got to remember that. Okay. You don't remember that, you'll never get through these inverse functions because you're going to be having to remember these special angles all the time. So what's the y here? Y'all just told me. What angle has sine 1/2? 30 degrees, or pi over 6. Yeah, let's give it in radians. Pi over 6. Is that in the proper range? Remember, you've got to come up with an angle in the proper range. Okay. The proper range for the arc sine function is minus pi over 2 to pi over 2. So is that in the right range? Yes. Yeah. Okay. So that's got to be it. That's got to be the answer. Let me ask you another one then. Looks almost the same. What about arc sine or sine inverse of minus 1/2? Okay. All right. So this has to be, it's got to be almost the same answer, right? All right. So let's call that y until we figure out what it is. So let's say sine inverse of minus 1/2 is equal to y. So that means what? Sine of y is equal to what? Minus 1/2. So now you have to just look at that and figure it out. What angle gives you sine minus 1/2? All right, now it's got to be negative, so we got to make sure we're in the right quadrant here, correct? So what would be y'all's first shot at that? It's 1/2. I mean, minus 1/2. If you take the absolute value, you get 1/2. So the reference angle has to be what? The reference angle has to be how much? Yeah, the reference angle has to be pi over 6 again, right? Okay, because you know, since the sine is minus 1/2, your angle is going to have something to do with pi over 6, correct? Okay, but you've got to get in the right quadrant. So, because you want negative, right? Well, where is sine negative? It's negative in the what? Third and fourth quadrant, right? Okay. Well, Fernando, we might try for the first thing that we can think of, which would be in the third quadrant. Third quadrant. So I would draw it right there because I want the reference angle to be how much? 30 or pi over 6, right? So there's an angle, the reference angle is pi over 6, but that's not the angle in the third quadrant. What's the angle in the third quadrant there? It's this whole angle, correct? Which would be what? 7 pi over 6? Yeah. So we're thinking, oh, the answer here is 7 pi over 6. Oh, I've got it. All right, so I'm done. But you're not done, because what was the mistake there? Where, what's the range for arc sine? Has to be between what? Minus pi over 2 and pi over 2, right? Okay, and 7 pi over 6 is way too big. So that's not what we're going to get. What now, Emil? Yeah, so we have to somehow get another angle here, right? What's another angle then? And I got to get in the white quadrant. So the third quadrant can't be it. Fourth quadrant. So we're thinking over here in the fourth quadrant, this angle, whose reference angle also would be pi over 6. But what angle is that, Fernando? If I draw the full angle, what angle is that? Yeah, I don't want to draw the angle positive, because that would be, how big is this angle that I just drew? It's almost 2 full revolutions, but it misses by pi over 6. What would that be? That would be 11 pi over 6, right? But that's too big. See, that's out of the range, correct? So, but Fernando, what was your suggestion? Take the negative angle, right? Yeah, okay. Take the negative angle, pi over 6. That still has the same reference angle, right? Okay. So instead of 7 pi over 6 or 11 pi over 6, try just plain old minus pi over 6, right? Okay. That would have pi over 6 as its reference angle. So the sign of that will be minus 1/2, because we're in the fourth quadrant. So that's got to be the right answer. This is why I was stressing it's important to remember the range of these inverse trig functions, okay? What does your calculator say, by the way? So your calculator will compute for you the arc sine, and usually you do that through, well, it depends on the calculator that you've got, okay? You might use a second function sine, okay, or shift with the sine, right, to get the arc sine. Negative 0.52, which I think is about pi over 6, yeah, okay. So in many instances, you will be just using your calculator to compute these inverse trig functions, okay. All right. Now we can pull this same trick now with all of the functions. So because none of them have inverses, and so we can make them into functions though that have inverses by restricting their domains. Okay, and so for cosine, we can also restrict its domain to get a function that has an inverse. However, we're going to restrict the domain slightly differently, so you have to keep this in mind. The restricted cosine function, its domain is 0 to pi, not minus pi over 2 to pi over 2, but 0 to pi. There's what the restricted cosine function looks like. So that's just a graph of the cosine curve, except I just cut it off from 0 to pi. And notice that's decreasing. That piece of the cosine curve is always decreasing. So this piece of the curve does have an inverse. So the restricted cosine curve does have an inverse. And there's what the inverse looks like. It's hard to, that one's hard to draw by hand. Okay, but that's what the inverse of the cosine looks like, called the arc cosine, or you can call it in more modern notation, cosine inverse. What is the range of, it's important now, the range of the cosine inverse, the arc cosine, the range. Here's the graph. Remember, the range is the y values, right? So what is the range for the arc cosine? What part of the y-axis? Starts where on the y-axis? What? On the y-axis. Where does that curve start at? What? 0, and goes up to where? Pi, right? Okay. So for the arc cosine function, its range is 0 to pi. So if you're evaluating arc cosine, which you will be doing in some of your problems, right? Remember, you have to get a result between 0 and pi. Okay. So if you get something outside of 0 and pi, you got to go back to the drawing board and come up with another angle, right, between 0 and pi. These are really the only two ranges that you have to remember. For the other four trig functions, they are based on these two ranges. So remember, for the sine function, the arc cosine function, the range is minus pi over 2 to pi over 2. For the arc cosine function, the range is 0 to pi. So if we pull the same game with the other four functions, tan, cotangent, secant, and cosecant, if we restrict their domains properly, we can come up with inverses for all of these functions. The ones that we really use a lot are arc sine, arc cosine, arc tangent, and also arc secant. That one is also useful. Less useful, arc cotangent and arc cosecant. All right. Now, again, remember, for all of these functions, how do they work? You put in what sort of quantity? A what? No, for the inverses, you put in a angle. You put in an angle and you get back a number. Remember, for the original trig functions, you put in an angle, you get out a number, right? Okay. Here you put in I'm sorry, I said it backwards. You put in a number and you get back what? Angle, right? Okay. But Hannah, I think you said it correctly. I said it. It's opposite of the original trig functions. And you do need to remember what size angle you're going to get back. In other words, what are the ranges of these functions? So we already mentioned for sine, it's minus pi over 2 to pi over 2. For cosine, it's 0 to pi. For tangent, it's back to minus pi over 2 to pi over 2. Which is the same as arc sine, right? The way to remember that is to remember the definition of tangent. How is tangent defined? Or how can you, not the way it's defined, but how can you compute it? Sine over what? Sine over cosine. And so sine there is on top. So sine is in control for tangent. And that means that for the arctangent, its range is going to be the same as it is for the arcsine. Minus pi over 2 to pi over 2. What about for cotangent, though? How can you compute cotangent? Cosine over sine, right. So for the cotangent, cosine is in control, so to speak. And so for the arc cotangent, its range is based on what the cosines is, which is 0 to pi. What about for secant? How can you compute secant? That's 1 over what? Cosine, right? So the range for the arc secant is the same as the range for the arc cosine, 0 to pi. And how do you compute cosecant? That's 1 over what? Sine, right? So the range for the arc cosecant is the same as it is for the arc sine, which is minus pi over 2 to pi over 2. Does that make any sense to y'all guys at all? All right. For the inverse trig functions, you must remember the ranges. That's crucial. But it's really only these two that you need to remember the range for. The others you can derive from these two. Oh, well, look, we're not going to make any progress without practicing this. So these functions do have graphs. These inverse functions do have graphs. The graphs are really not important to us. The only one that you ever refer to again that I can recall is the graph of the arctangent. There's graph of the arctangent. And it's interesting because of what happens on the far left. I'm sorry, on the far right here. As the inputs get really big, the arctangent goes up to, but does not exceed pi over 2. That fact sometimes becomes useful. All right, let's practice. So we already practiced a couple of them. Let's try a few more before we stop here. So what about sine inverse or arc sine of 3/2? This is a trick question. So what's the answer there? We can figure that out quickly. Remember, you put in a number, right? And you get back a what? Angle. So the answer here is an angle whose sine is 3/2. But does that ever happen? How big does sine get? What's the biggest sine gets? Now, when you compute sine of something, what's the largest value you get? 1, right? Remember, the graph only goes up to what? 1, correct? Right? It goes down to -1. You cannot have sine of an angle ever being 3/2. So the answer here is this is undefined. Yeah, right. Your calculator said error there. Yeah. Go away, HP support. All right. So this is undefined. So now it's turned off my pen. Trouble for such an answer there. See if it's back on. No. All right, so this one is this one's going to be undefined. Let's see. Let's write it out. Not very good with the mouse. Triangle right there. Let's try this one then. We may have to just talk through it. What about arc cosine of square root of 3/2? Okay. So arc cosine of square root of 3/2. How does that have to work? Let me try another. Here. No. Yeah. What's your reasoning there? Whoever said. What now? Oh, darn it. Okay. Disappointed me. Sorry. All right. Well, so so without a calculator, how could we reason this? So again, just call this temporarily. Just call this temporarily y. All right. So just write. Let me write it on the board. All right. So for you guys at home, you're just going to have to be patient here for a second. I've lost the pen. All right. So we have cosine inverse of square root of 3/2. Just momentarily think of that as y. All right. And what you know about y is that the cosine of y has to be square root of 2. All right. So you just have to recall from your knowledge of angles, hopefully this will be a special angle, what angle has cosine square root of 3/2, right? So if you remember my little tricks here for remembering sines and cosines of special angles, you can figure this out. Cosine begins at what? At 0, cosine is what? 1, which is square root of 4/2. And then count down. So pi/6, cosine of that would be square root of 3/2. So you count down 1 under the square root. Well, there it is, right? Okay. So we know the y here must be, well, yeah, whatever you're on here, must be pi/6. What about cosine inverse of 0? So our arc cosine of 0. Is it 1? I don't think so. Remember, Emil, from arc cosine, you put a number in and you get what sort of thing out? What sort of creature out? You get an angle, right? Keep that in mind. Remember, for cosine, you put in an angle, you get a number. For inverse cosine, you put in a number, you get back an angle. So you're going to give me an angle here is the answer, right? So, but the answer you want is what angle has cosine 0? Then you just have to recall this, all right? So what angle has cosine 0? It's not 0 because cosine of 0 is 1. So you know the answer isn't 1 there, right? Okay. So what is it? Pi over 2, right? Okay. So again, just temporarily call that answer y. You don't know what y is, but you know cosine of y has to be 0, and it is pi over 2. Right? Okay. Cosine of 0 is 1, so cosine starts at 1 and goes down and hits 0 at pi over 2 at 90 degrees pi over 2. So answer pi over 2. All right, well, since okay, since y'all are desperate here, I'll let you to use your calculator. Use your calculators for me, all right? Because many times we'll have to use the calculator, all right? So try computing these, all right? And these you'll have to use the calculator. These are not special angles. So just what does your calculator say is arc sine of minus 0.82. Remember, these are radians, so be sure your calculator's in radian mode, okay? While y'all are computing those, let me see if I can get the pen to reconnect. So this is just, do you know how to this is just, do you know how to use your calculator, basically. Can y'all do this on your calculators? Is there anybody who's having trouble with that on your calculator? Yeah, I really cannot get it to, I get pen to respond. But I think I have another, I have to restart it to get it to respond. I think I have another stylus though, so let me reach for that. Oh, so that's right. Okay, so just try these. There's at least one tricky one in here though. So you'll probably get calculator will probably explode or one of these. All right, so let's try this. What y'all get for approximately, what's the arc sine of minus 0.82? What, 1.32? Sounds good to me. 1.32. Okay. Y'all get the same thing? Were y'all able to get that? Can you use your calculator for doing that? You'll need to be able to use your calculator, so if you're having trouble with that, let me know. What about the arc cosine of 0.25? Oh, yeah, Jay. What?
Oh, no. It's negative.
Oh. Oh, okay. Yeah, it makes sense. That should be negative, right? All right, so minus 0.96. Okay, so slight correction there for you guys at home. Minus 0.96 there. All right, what about for arc cosine of 0.25? That's something, that's 1 point what? 1.32. Okay. So this is a trick question, right? Because what's the arc cosine of 1.25? Undefined, right? Remember, you will never have cosine of an angle as bigger than 1, right? So you can see immediately that's not going to work. But now you can have tangent of angles being 125. So this is not going to come out as undefined. What's the arc tangent of 125 approximately? What now? Oh, so it's not even very big. 1.56. All right. So don't automatically assume that this one is going to be undefined also. Let me fill in there let me fill in what I messed up here before. So let's see. This is undefined, right? Define. This was pi over 6. This is pi over 2. And now let's do one more, because we got just one more example here. And we'll stop for today. So let's try this one. All right, so we tried this one for sine. Let's try it for cosine. Arc cosine of -1/2. All right. So again, let's call this y. And we know that the cosine of y has got to be -1/2. Let's think about reference angles first. So forget about the sine for a moment. What angle, what's just angle between 0 and 90 degrees? That's not going to be the answer here, but that will help us with the reference angle. What angle between 0 and 90 degrees has cosine 1/2? Just forget about the sine for a moment. So where is cosine 1/2? Let's see, pi over 3, right? Okay. A cosine of 0 is 1, and then at pi over 6, it goes down to square root of 3 over 2, and then at pi over 4, it goes to square root of 2 over 2, and then at pi over 3, it goes down finally to square root of 1 over 2, which is 1/2. So you know the reference angle here is pi over 3, but the answer here is so pi over 3, right? But the answer is not pi over 3, because the cosine of pi over 3 is positive 1/2, right? So we have to have an angle that has this reference angle, but we have to get the cosine to be negative. All right, so that means we got to get in the right quadrant, correct? But where is cosine negative? Second and the third. I think second is where we want, right? However, because we want an angle between 0 and pi. So if we went into the third quadrant, we would have an angle that's too big. So what angle in the second quadrant has reference angle pi over 3? Well, you want the reference angle to be pi over 3. So you want this angle to be pi over 3, right? So what's the big angle here? 2 pi over 3? There we go. So it looks like our answer there is 2 pi over 3, right? Pi over 3 short of 1 pi. So let's fill it in. 2 pi. That's in the right range, right? 0 to pi. And I think if you compute cosine of 2 pi over 3, yeah, the answer was -1. Okay. Well, that's how inverse trig functions are going to work. All right. You basically get the idea. They're not always so easy to evaluate, though, right? So it does take lots of practice to get comfortable with them. But we do want to. The reason that we want to understand the inverse of cosine functions is it's going to help us solve equations the inverses of trig functions is it's going to help us solve equations that involve trig functions. Because remember, what happens for all functions, right? For all functions, so trig or not, what happens when you compose a function with its inverse. You get what? Not one, but like one, Jad. Almost X. Right, yeah, okay, right. When you compose a function with its inverse, remember they cancel each other, right? And you'll just get here X. So that property is also true for inverse trig functions. And we're going to make great use of that property and helping us solve equations. Okay, certain types of equations. All right. Well, let's stop there. See if I can save my pen. All right. So we did a lot today because we didn't do a lot of classwork. So it was a lot of me talking. Sorry about that. Next time I'll try to make things a little bit more active. So on Monday, we're going to mention, as I mentioned, we'll continue talking about inverse trig functions, but we're going to do a little bit of the sample test, but not all of the sample test. And I will post the answers to the sample test sometime this weekend. Okay, so I'll send an email when those go up. A week from today, yeah, okay. So start working on that. Start working on that sample test. It doesn't include any of this. All right. See y'all Monday. Y'all very good today. Thanks.
Windows support for your test.
Oh yeah, I can do so. I stop touching that. I know. All right. Good idea. I don't know if I haven't tried, but I probably. Yeah, I mean you should be able to, right? So. All right. Thanks. All right, guys at home, we're done. I'm turning off the share here. Whoops. Let me. Bye.